Task 1. I have split the existing controller state machine into two, feeder controller and transfer controller, and designed the protocol to connect each other. Feeder unit pushes the item from magazine to other end, after which it retracts back to the normal position. There are three inputs to the controller: POS_E, POS_R, and empty, from the feeder unit. Based on the status of these inputs, it will trigger the next state. Feeder only pushes an item when the push signal is given by the transfer controller. A pushed event is emitted when an item is pushed to the other end by the feeder controller. Transfer unit picks the item from the magazine end and drops it to the other end. According to the three inputs, @_MGZ, @_next and VN, various states are reached. Controller only picks the item when the pick signal is given by any other controller, feeder or transfer. An event dropped will be raised after transfer unit drops the item. Plant is controlled by two controllers, feeder and transfer. These two controllers are connected to each other by event input and event output, i.e. feeder controller's event output, pushed, is connected to event input pick of transfer, and transfer controller's event output dropped is connected to event input, push, of feeder. Feeder control emits an event push to the event input pick of the transfer controller. This helps the transfer controller to know whether any item is present to be picked from the magazine end. Transfer control emits an event drop to the event input push of the feeder controller. This helps the feeder controller to know whether any item is to be pushed. In this case, our protocol easily fits to the topology. Controllers can easily communicate using the event inputs and event outputs. In this scenario, the feeder unit pushes an item only if the magazine is not empty, and emits an output event push to the transfer controller's input event pick. Once the pick event is triggered, then the transfer controller picks the item and drops it. After that, the transfer controller generates an event drop to any other controller. In this case, it is another transfer controller. It listens to the pick event to be generated, and once it is generated, it will pick the item and drop it to the other end. This transfer control also generates the dropped event output and is given to the feeder controller's push event input. Feeder unit again pushes an item only if the push signal is triggered by the last transfer controller. This process will continue to work until the magazine is empty. Distribution station, filling station scenario. The feeder and transfer controllers can be easily integrated and packaged. Using the feeder transfer configuration, we can build the distribution station. The same way we can build the filling station with transfer feeder configuration. This distribution station and filling station assemblies can be directly connected with the help of input events and output events. Now, let's watch the demo. HMI integration. The same configurations can be implemented with HMI. The data inputs like start, AC, reset, and stop are used to control the plant. Based on this input, the feeder controller will generate appropriate conditions of the plant using blinking LEDs. The feeder controller emits proper event inputs and data inputs and makes sure that the plant works perfectly without any failures. Here, I integrated HMI with a feeder controller. Likewise, it is possible to integrate a separate HMI for the transfer controller. The plant is controlled by two controllers, feeder and transfer. These two controllers are connected to each other by event input and event output, i.e. feeder controller's event output, pushed, is connected to event input pick of transfer, and transfer controller's event output dropped is connected to event input, push, of feeder. Feeder control emits an event push to the event input pick of the transfer controller. This helps the transfer controller to know whether any item is present to be picked from the magazine end. Transfer control emits an event drop to the event input push of the feeder controller. This helps the feeder controller to know whether any item is to be pushed. Now, let's watch the demo. Task 2. First, we need to make sure that the core functionality of each function block, FB, works perfectly. Core functionalities can be tested using a unit testing approach. If we are able to pass the unit tests, then we can go for further levels of testing. Here, I developed 2 unit test cases for demux FB and in-range FB. In demux FB unit testing, we will be verifying whether the given data is demultiplexed. If it is demultiplexed correctly, then the test case will be passed and the result will show true, otherwise the result will be false. In the case of in-range FB testing, we will be verifying that the given number is in the given range. Like the previous examples, the core functionality of individual basic functional blocks can be tested and make sure that everything works perfectly as we expected. The control logic of controllers also can be tested by adding an additional test functional block. The control logic to detect deadlock using an additional functional block can be implemented by converting deadlock detection algorithms to control logic, execution control chart. Design and verification in deadlock detection for connected controllers are more complicated and difficult to implement as an additional functional block. Path identification and counterexample generation for deadlock detection in concurrent system implementation can be developed using NuSMV. Simulation and testing using NuSMV. For testing all possible button pressing combinations of input and to detect deadlocks, I took execution control charts of feeder controller and transfer controller. This control logic needs to be converted to NuSMV program for exhaustive testing. NuSMV code. Simulating the SMV code on interactive mode gives us the provision to go through each state by giving appropriate sensor inputs. We can try all possible button pressing combinations to verify whether the system behaves as we expected. We can also randomly simulate the traces, or we can manually go through each state by selecting different input combinations. Testing and simulation can show the presence of bugs, not their absence. The NuSMV testing can also be done by checking various properties, i.e., we can test the statements whether it is true or not in all possible execution traces of control logic. This will give us the opportunity to test critical scenarios where there can be failures in some combination of inputs. Invariant property test. Checking invariant properties helps understand whether there is a reachable state that is also a bad state. In this case, we ensure that to_next and to_mgz outputs of the transfer controller should not be true at any point of time. Affity property test. Safety property is used to detect something bad that can happen during any trace of its execution. For example, we need to verify that the feeder should not push the item when the magazine is empty. This can be ensured by the following command. This command checks that if the magazine is empty, then the next state retract signal should be true. In this case, we ensure that when the magazine is not empty and start input is given, then the feeder should push the item at any circumstances. Liveness property test. Something desirable will eventually happen. Whenever a feeder pushes an item, transfer will always pick it. sooner or later. Liveness property is used to identify the deadlocks. We need to apply liveness property to make our control logic deadlock free. If the property satisfies, then it will return true, otherwise it shows a counterexample that contradicts our expectation. If any counterexample is produced by NuSMV, then we could debug and identify deadlocks. Liveness property means something good will happen infinitely often. Liveness property can test individual control logic, i.e. for feeder and transfer controller. In case of transfer controller's functionality is to pick an item and drop to the other end when the feeder pushes an item. To ensure that our control logic is deadlock free, we need to check that our core functionalities should occur infinitely often. In this scenario, whenever a feeder pushes an item, transfer will always pick it. Task 3. Considering the system as a black box, we can deduce the behavior of a finite state machine, FSM, using the input-output signals. Recurrent neural networks, RNNs, are an effective representation of control logic for a wide range of problems. Implementing an RNN in TensorFlow, or can use the ML libraries, based on input/output signals, can be used to extract the behavior of FSM. This is a sample code to create a model using RNN based on the input and output data of control logic. Sequences of sensor signal data input and corresponding output are given to RNN for creating the model. Decreasing the cost function is important to get a more efficient RNN model. This will help to get better control logic with a minimum number of states. We can transform the model by injecting some efficient encoding network to the RNN model. Here we have to identify a better encoder network that can be inserted into the trained RNN model to extract the finite state representation. This encoder network can be trained to get an accurate finite state representation with minimal loss of information from the recurrent neural network. After extracting the finite state representation from the RNN model, we need to do the minimization process. In the minimization process, we can apply state reduction techniques to get an optimal solution. Another approach for constructing control logic is from rule-based algorithms. Drip or part algorithm can be used to construct rules based on the sensor inputs. Analyzing these rules gives us a basic understanding of the system's working behavior. It is possible to extract the control logic from this set of rules to an extent. An optimal solution will give us a minimum set of rules. This will help to create more efficient control logic. Extracting the control logic from this set of rules will be a difficult task. I have randomly generated sensor input data and output data for the feeder controller. This data set is a completely random one and has no relation to our feeder controller's behavior. Using the part algorithm, I have created a decision list. This set of rules will help to extract the control logic of the system. We can create a model for each output. Each model will give us a decision list. By analyzing these sets of rules and applying some intelligence, maybe it is possible to extract the control logic to a greater extent.